Hey Fizz kids, Mr. C here, and we're going to talk a little bit more about torque today, except now we're going to start moving away from statics and whenever our net torque is zero, and what happens whenever we do have some sort of net torque acting on our system. But before we talk about that, we first need to understand a few other concepts. The key question to all of this is: does mass resist rotation the way does mass resist rotation the way it resists acceleration? So, like mass doesn't want to accelerate, it doesn't want to move. That's why we have to apply a force. Is rotation the same way? Do things not want to rotate if they don't have to? And the answer to this is actually yes. And it all has to do with a rotational inertia. And every object has this rotational inertia, but all it is it's your resistance to change motion. And whenever we talk about rotational inertia specifically, it's the resistance to change its rotational motion. So just normal inertia is sort of generalized. It's all motion. And we use this specifically whenever we talk about moving in a straight line. The larger your mass, the more inertia you have, and the less likely you're going to move. The same thing goes for rotational inertia. The more mass you have, the less you want to start rotating. But the thing with rotational inertia is it also depends on a couple other variables as well. And we're going to talk about those in a second. And well, now I guess. But rotational inertia, like I said, depends on mass, but it also depends on where that mass is located. So if mass is, say, like at the very, very far ends, it might be a little bit harder to rotate than whenever mass is really, really, really close together. So you have to look at both how much that total mass is, and where the mass is actually physically located on the object that you want to start rotating. We find that whenever we do a whole bunch of really cool math that you can actually do with calculus later on, but we end up finding out that the rotational inertia is going to be proportional to the mass times the radius squared. And that radius is measured from the axis of rotation. So like I said, it's dependent on the mass, but it's also dependent on the radius squared. So that radius really plays a very, very large role, because if you just double your radius, say, you're actually quadrupling your rotational inertia. Whereas if you double the mass, you're only doubling the rotational inertia. Whenever we have objects that are rotating, we can describe them using both rotational kinematics or rotational motion variables, or we can describe them using linear variables. Whenever we have a torque that's applied to an object, so like we know a torque is just some force applied from some distance r from our pivot point, we create an angular acceleration. This is only when we have a net torque. And we say our angular acceleration is going to be symbolized with this Greek letter alpha. Whenever we talk about our linear motion variables, though, we have acceleration, we have mass, and we have force. And those are our three big variables. And we also have like things like velocity and stuff like that. Uh, and those are all very useful with linear motion, but they all have an equivalent with the rotational motion variables. And in this case, the rotational equivalent of acceleration is just an angular acceleration. So it's just how fast we're accelerating in our rotational motion. Where we would use mass a lot of times with linear variables, we're actually going to be using rotational inertia. So it depends on that mr squared. So that's where we have like inertia, normal inertia, which is just dependent on mass. And we have rotational inertia, which is dependent on that mr squared factor. And then finally, in our linear variables, we have forces. Well, whenever we talk about rotational motion, well, force plays a part, yes. Torque is actually the more important force here. So these are sort of the variables that we'll be using, and they're equivalent. And like I said, whenever we started rotation, everything that we talked about before in linear motion has a rotational equivalent. So like acceleration has angular acceleration. We're going to learn later on that even velocity, you can have angular velocity, or you can have angular displacement. Force goes to torque. Mass is rotational inertia. Even with things like momentum and energy. With momentum, you have angular momentum. With energy, you have rotational energy. So they all have an equivalent, and they're all pretty much the exact same. You just a different variable and be calculated in a slightly different way, but the principles all still apply. They all still follow the same rules that we learned all the way back in first quarter. The first variable that we are going to look at in this video, because it does matter, because we're talking about net torque. So a net torque does imply that we have some sort of net force acting on our system. And forces are all concerned with acceleration, but just we actually can relate linear acceleration to angular acceleration. So even though they are different things, they're still relatable. They're still, they still have some sort of relation. They're still dependent on each other. And in this case, we know that our linear acceleration, or that a that we're so used to working with, is just going to be equal to our angular acceleration times whatever the radius of the motion is. Or if you want to look at it another way, uh, boy, that was a bad alpha. Alpha is going to be equal to a over r. This is one equation that's not going to be on the equation sheet. So this is something you just kind of got to keep in the back of your mind, that your linear acceleration is equal to your angular acceleration times the radius of motion, because it's not going to be something that's given to you on the test. But this one's not that hard to remember. And we're going to learn about the other conversions later whenever we talk more about kinematics. But right now, whenever we're talking about net torque and we're talking about angular acceleration, the only linear variable we really need to focus on is just our normal linear acceleration. To put the equation into rotational motion variables, the force, like I said, is replaced with the torque about the center of mass, and the linear acceleration is replaced by the angular acceleration. Like I said, it's just flipping out. So if we look here at Newton's second law, my favorite, it's written as A equals F over M here, but you guys a lot of times see it as F is equal to ma, my favorite, Newton's second law. I love this law. It's the basis of Newtonian physics as we know. But Newton's second law has a rotational equivalent. In this case, our rotational equivalent is going to be alpha is equal to torque divided by mr squared. And like I said, the rotational equivalent of our acceleration is alpha, so we just flip them out nice and easy. The rotational equivalent of force is torque. Once again, we flip it out nice and easy. And then the rotational equivalent of mass is mr squared, or that rotational inertia. So we just flip that out again. And this law still applies. So whenever you have a net torque, it's just equal to alpha times mr squared. Or another way that I like to write this is torque is equal to I alpha, because this whole term here is just your rotational inertia, or your moment of inertia there. Kind of crazy to think about it like that. It's kind of cool. So Newton's second law for torque is the same as Newton's second law for linear motion. We just flip out. We replace those linear variables with our rotational variables. And we're going to do a whole bunch of example problems with this TI alpha, as I call it, the TI alpha rule, just to show you how it works. So don't worry, if you don't quite see it now, we're not going to do an example problem in this video, but we're going to save all that for whenever we come into class. The last thing I'm going to kind of talk about now is the moment of inertia, or what's the difference between the moment of inertia and the rotational inertia? Well, if you have multiple objects, whenever you add up all of those objects' rotational inertias, you get what you call the moment of inertia. So the moment of inertia is just whenever you add up all of the different objects on your whatever your rotating object is, you add up all of their moments of inertia, and then you get what the total moment of inertia. So the moment of inertia is all of the different masses combined together, and you're looking at what their moment of inertia is, whereas the rotational inertia is just looking maybe for just one object. And in this case, the moment of inertia is just the sum of all of the individual rotational inertias of that object. Because rotational inertia depends on the square of the radius, the distribution of the mass makes a huge difference for solid objects. That's why, and we're going to talk more about this in class, but if you have a solid disk and you have, say, a hollow disk, but they're the same mass, it's just the mass is distributed differently, their moment of inertia is going to be drastically different from each other, which is crazy to think about. But like I said, we're going to talk more about that in class. And yes, like I said in class, different objects have different moments of inertia, different moments, and we're going to talk about all that in class because that's just a little more complicated than what I want to go in on this video. So make sure that you answer all the questions in this video, and I will see you whenever we come in class, and we'll talk more about torque, rotational inertia, and TI alpha stuff, and then we'll also talk more about moments of inertia and what that means for us in physics. So I'll see you guys later.